Hi, my name is Jacob Wood. The purpose of this video is to test the microcontroller block within the Smart Luggage Design project. You can see here the block description document for the microcontroller block, and throughout the testing procedure I will reference this document. You can see the block description here, a block diagram and corresponding interfaces and properties. Continue scrolling down and we can see some wiring diagrams followed by testing procedures that I will follow directly, and finally some validation for the interface properties. First, we're going to test the power supply to the microcontroller block. We're going to do this by setting up the minimum and maximum input voltages and current limits to the microcontroller block and see if we will boot on, and make sure that we are not going over our peak current of 1 amp. You can see on the power supply what we are pulling in amperage on the left and the voltage remaining the same at the minimum 4.75 volts. We can see that our Pi has fully booted on here. Now we will administer the same test using the maximum 5.25 input voltage, maintaining that we are not pulling over or reaching that 1 amp current, peak current on the left side of the power supply there. And we can see again that we are booting up on the monitor here, and we are on. To test the minimum required power going to the sensing blocks, we will pull power from the 5-volt rail, which will be powering the sensing blocks. You can see those on the sensing blocks on the right. And we run this to a dynamic load through a DMM to see that we can pull at least 30 milliamps, which is the combined parallel amperage rating of the sensing block. So we will run this test for 30 seconds to make sure that we can, in fact, get 30 milliamps nominal from the microcontroller block. This test also passes because we require 5 volts to operate the sensing blocks as well, and you can see on the dynamic load that we are pulling indeed 5 volts. To test the minimum echo signal duration from the ultrasonic block to the microcontroller, we will set a solid object within 5 centimeters of the sensors, power the device at least 5 volts. Then we will run our testing script to capture measurements to that closest object, which is the obstacle we put here. We're going to probe that echo line and take a screenshot of one of these echo return signals and make sure that it is within 300 microseconds. To test the maximum echo pulse duration on the same echo line, we're going to set up an object, solid reflecting object, 200 centimeters away from the sensors, power the device on, and run our measurement script again. And again, we will probe that echo line on the oscilloscope and take a screenshot, and this should be within 12 microseconds at 200 centimeters, and you can see there that it's within that. Finally, to test the minimum trigger signal duration to start a measurement, we're simply going to probe the trigger line to the sensing block, power the block, run our testing script that actually sends this trigger signal, and measure it to see if we can trigger the measurement with something less than 10 microsecond trigger pulse. And you can see here that we just did so. To test the 10-bit precision on the IR sensing block, we will use the IR sensor with a testing script from our Raspberry Pi, set its voltage to about 5.2 volts, and run our testing script, and I'll probe the output of the ADC block going back to the Raspberry Pi, and I'll take a screenshot of this output so we can see the serial data being clocked out. If we study the datasheet for the ADC block using the SPI interface, we can see this D out or data out bus, and what we should see is a null bit followed by the 10-bit precision, so 10 bits for one clock cycle each. Now, the way that this is sent back and forth is in 8-bit segments, so one of these bits, as you can see here, bit 7, will actually be held for 2 clock cycles. So we should actually see 10 bits on the oscilloscope, where 1 bit is actually being held for twice as long as the rest of the bits. So we can now look at our output on the oscilloscope. So here is the captured output waveform from the data out bus on that ADC module. And so when we zoom in here, we can actually see the clock pulses, the sharp vertical lines in this block of data. So we can actually count these, and you can see there'll be 1, 2, and then a gap at that third value. So when all is said and done, there will be 10 of these pulses within this value that we can count, and you can see them here. Next, I'll verify that the ADC module and IR sensing block has at least two available output channels. So you can see here I have a testing script that's actually printing out the values on two of the 8 channels on the block. And what I'm going to do is supply 5.2 volts to the block and probe the output of the block. And so these are actually 2 different values being probed after a second. And so you can see channel 0 is being printed. I'm going to switch to channel 1 right here, and now we can see that channel 1 is being printed and channel 0 is just collecting a little bit of noise. To verify that we are communicating with the IR block using the SPI protocol, I'm going to scope the master in, slave out, and master out, slave in buses between the microcontroller and the block itself. I'm going to supply the block 5.2 volts and run our measuring testing script. And you can see we're capturing and converting some measurements, and right here you'll see in the blue is the master out, slave in, and the yellow is the master in, slave out bus. And we'll check the data sheet. So in looking at this data sheet, we should expect to see on the master in, slave out bus a start bit followed by some control bits, and that'll actually just be we'll see 1 1 in those control bits, and the rest is don't cares, and those don't cares are actually just going to be 2 bytes of just 0. So we'll just see those being driven low. And on the master in, slave out will be the data leaving the IR module, and so we should actually see some varying 10-bit data there, and so we can check our outputted waveform. So here our output waveform confirms what we expected to see based on the data sheet. The blue line is sending a start bit, 1 control bit, and then the rest are don't cares, which are driven low. You can see our yellow line, which is actually our data back to the microcontroller, is if we zoomed in, it's 10 bits long, and leading up to it, it's just don't care as well. To test the signal between the alarm block and the microcontroller, we are going to power the block, or the alarm block, through the microcontroller, measure the nominal voltage on the right, which is sitting at about 3.3 volts, and on the left we have the nominal current, 5.3 milliamps. And we run this test for 30 seconds to maintain that these nominal values are in fact correct. And we don't want to reach our maximum voltage of about 10 volts, or 5 volts and 10 milliamps. To test the code and camera interfaces, we have connected the Raspberry Pi to the camera with the 15-pin ribbon cable. You can see we're probing that operating voltage of about 3.4 volts nominal to operate the camera. And here you can see the output of the camera, where it is outputting the frame depth and the resolution, which meets the requirement as well. And that top screen, you can see a freeze frame of the camera input, so we are in fact receiving camera input as well.